Um, yeah, today I'm going to talk about joint work I did with Jens Palsberg while I was at UCLA as a graduate student on a formalization of Java's concurrent access modes. So a little bit of background. Processor manufacturers have been stuffing cores onto processors as a consequence of kind of diminishing single-threaded performance gains. And so as a consequence, programmers are they need to leverage this to get those performance gains, and they do that in many different ways, but one of the ways that they do it is through shared memory concurrency. And this appears in lots of different languages, but it certainly appears in Java. So in 2005, if you can remember back to 2005, Manson and co. Wrote this paper formalizing Java's memory model. And this was pretty early work, and actually for the time it was pretty great. But it was pretty hard to understand, and there wasn't a really direct way to check the behavior of actual programs. So in the intervening time, there's been lots of progress on weak memory model research. Lots of good tools, lots of interesting formalizations of various hardware specifications and languages. And but a lot of that has been outside the realm of Java. It's been mostly with C11 and hardware. So in the JDK version 9, they added a new API for concurrency, and it uses what's called memory order modes. And shortly after that, in November, well, I guess it's in 2018, they also released an informal specification for the semantics of these modes. Broadly, it's meant to sort of emulate or is inspired by C11's memory orders. But basically, the informal specification is intended to solve three problems that arise when you have a poorly specified semantics in this context. One of them is that programmers tend to make architecture-specific assumptions in the way they write their programs, so their programs tend not to be portable. A lot of times they don't have enough synchronization, so their programs are incorrect. Alternately, they may be unsure of what they're doing, and so they over-synchronize and ends up in slow code. And remember, the whole point of this is for performance. A little more detail. So the VarHandle API comes as in these access modes, as I mentioned. It starts with a plain access mode, and this is just what you're used to looking at in normal Java code, which is variables. So in this case, the variable y is shared, and it's just accessed via normal reads and writes. Opaque mode, which is slightly stronger, gives slightly more guarantees. In particular, it gives this acyclic causality guarantee, which we'll talk about a little bit later. Release acquire mode, which you'll be familiar with from sort of message passing, locks, this kind of programs. And then finally, volatile mode, which is basically the semantics of volatile variables, which pre-existed this API. So broadly speaking, the idea is that, just similar to C11 memory order modes, is that as you use stronger modes, so as you kind of go down this list, you get strictly more guarantees about the access that you're decorating with the mode. And this property is known as monotonicity, and we prove this as a theorem. I'll talk about that a little bit later. So this informal specification has a couple problems that you would expect from an informal specification. One, it's ambiguous. So if you go and read it, there's a lot of confusing prose. It's hard to know what a program will do just from reading the specification. It's not executable. So if you have a small example program, or even a small example program, tiny one, to demonstrate like maybe what's going on in your program, there's no way to kind of run your program using the semantics. And there's lots of properties that are defined in the specification, which are to deal with programmer disciplines and the guarantees that they give you, which remain unproven. So our work provides solutions to these problems. We provide a formal axiomatic semantics for the specification, which is obviously not ambiguous because it's formal. We have an instantiation of the semantics using a tool called herd, which allows us to execute small programs exhaustively and then consult our model to see if any of the executions are possible under our model. And along with that, we created a fairly large test suite of programs, which we'll talk about. And then to address the fact that there's these unproven properties, we also formalized our model, or instantiated our model in Coq, and then built a meta theory around it. Okay, so let's talk a little bit about the semantics. First, it formalizes all of the parts of Java's access modes, from the modes to fences, which are also in their anatomic read writes. We call it the jam for short. And if you're familiar with memory model research, one question you may have is, if there's been all this intervening research, why not use something off the shelf? We'll talk about the features that make that this a good opportunity to do something new. And then finally, I'll give you a flavor of like the two core relations in the semantics that make it work. So to start, let's address this question about why not use an existing model. So as I mentioned about opaque mode, one particular feature of in the informal specification that's very clear about is that it has this property called acyclic causality. And what does that mean? Well, if you look at a program here, you'll see a read of x can then flow to a write of y in the thread on the left, and then a read of the y the value read by y on the right may flow to x. And so you have this kind of weird relationship between the variables. And the question is, can these always take the same value for an arbitrary value? And in axiomatic semantics, in our semantics, the axioms are over executions, which take the form of graphs. So it's worth kind of taking, like most of the examples I give in this presentation will look like this, so it's worth taking a second. So these graphs have nodes, which are basically labeled accesses, memory accesses over variables for values. There's relations like here's program order, which encodes the sequencing of instructions in the program, and then reads from, which encodes when a read is read from a write. So again, the question is, when you look at this graph, the question is, or rather the answer is yes, these two variables can take the same value for any n. And the question, and the way to get that is essentially this cycle, where you have this cycle of program order and reads from. You can kind of follow it along there. And what that kind of intuitively means is that the read is affecting its own execution, which is sort of silly, right? So, but there's basically a decade or more of research on dealing with this problem because it's rather subtle. This is a simple example, but Java basically forbids these types of executions out of hand. The downside is there are other programs which rely on exactly these cycles that are totally reasonable. So in this case, the write to y or the read to x, or the write to x on the right side could be reordered above the two reads, in which case it would still exhibit that cycle, but that's a thing that regular processors and compilers do all the time. So this is also forbidden, but it's an execution you would expect in an optimizing compiler or hardware. The other big change that's again very clear in the specification is that the coherence order in the model is non-total. So what does that mean? Writes, so the coherence order is an ordering over writes to the same location. And most languages, most architectures provide a total ordering. And intuitively what that means is that if any given moment in time, at a split second in time, if two threads happen to inspect what's at that memory location, they can get the same answer. So what Java's, the specification is doing here is it's saying you no longer get that guarantee, which is seemingly a big deal. It gives us sort of a split brain notion of state to these variables. So, and this affects not only just like this intuitive notion of writes, but also it affects the definition of atomic read writes. And finally, why not C11? Again, I mentioned that the access modes are inspired by the memory order modes of C11. Why not just take C11 and make that the memory model? Well, there's some features that have been removed from the specification for Java, like release sequences and consume, release, consume, which are fairly complicated. You shouldn't understand what this graph is doing. It's only there to show that it is complicated. So examples like this is a release sequence. The blue ordering there from A to D is given by basically this idea of release sequences, and this is just sort of left out of Java's guarantees. So taken together, this is basically a big opportunity to look at memory models and try and do something a little bit simpler because they tend to be fairly complicated. So that's what we did. We took a big step back. We figured, okay, we're removing some features here. We're getting rid of some really big problems in terms of acyclic causality, so maybe we can do something simpler. And we started with like the simple idea of like what a memory model does. And in particular, a memory model tells you what values a read in your program can see when it executes. And in the context of in these execution graphs, it's the pairings of reads and writes. And then just take it a little bit further, because it's an axiomatic semantics, basically which executions are allowed by our axioms. So which pairs create valid executions, which read-write pairs in the RF relation create valid executions. So we have basically two relationships. So the one I mentioned earlier was coherence, and the only way to forbid executions in our axiomatic semantics is by creating a cycle in the coherence order. Basically, we say a write can't execute before itself. The second one is visibility, and the idea is very intuitive, which is just that when are the effects of one access visible to another? So this is vaguely similar to something, if you're familiar with C11, this is vaguely similar to happens before, though not the same. So let's take a look at some examples of visibility. So a few things are just sort of baseline visible in our semantics. First and foremost, when something reads from something else, the effects of the write are available to the read. They're visible to the read. Second, same variable accesses in program order are also visible to each other. So that's just a baseline of visibility. We extend this basic notion to cover essentially fences, opaque accesses, release acquire accesses, and volatile. So basically everything's defined in terms of this basic notion of visibility. Everything generates visibility relationships. So as an example, if you have a release acquire program here, so in this small program, this is a message passing program. The idea is that there's some work that's being performed. So you have a write to X, that is the work here. There's a read here that communicates the work has completed. And then the question is, can this read in the other thread see that the work was completed as you would expect it to? If we make this write a release write and the read an acquire read, it gives us this ordering relationship. So it generates these visibility edges. And then again, remember we said that the reads from relationship also generates visibility. And so transitively we have this visibility relationship, which would seem to suggest that it can indeed see that the work was done. So take a snapshot of this, put it in your mind because we're going to use it in a second. The second thing is coherence. So there's 4 kind of classical rules of coherence. I'll give you one because we'll use it in a second. Basically what this says is if you look at C as a read, and it read from B, but it was also aware of A. And so the edge that this gives you a coherence order edge. It says that A came before B. Intuitively, the idea is that a read can't read from something in the past, right? So there's some overwrite, which is B. So it can't go back in time to read A. So it should be ordered before B. Hopefully that didn't sound like gibberish, but the idea is that it should just read the most recent write. So it gives us that coherence order edge. Okay, so putting this all together, we need to eliminate executions, right? So let's take our message passing example, and we're going to demonstrate that in this case where it sees the work that's completed, it can't read from initialization. So first we take the read from initialization. Now we need to show that this execution is basically impossible. So we use that rule that we just had. We take A, B, and C, and we just basically substitute in there. So we say that D read from the init, and that write to A was also visible. And again, I skipped over this, but if you look at the coherence order that's already there, basically initialization writes should come before all other writes. And then we substitute in using the rule, the coherence order rule, and then up at the top there you see a cycle. What essentially means is that in this case, A came before itself, right, which we don't allow. So the execution is not allowed. So this is it. I mean, the only difference between what I've shown you here and what's in the semantics is just some additional rules for generating visibility order edges and some additional rules for generating coherence order edges that are comport with existing memory model research. So we define a semantics, and I'm claiming it's Java. Obviously, we should probably do some validation. So one thing we did is we instantiated this for herd. We have a suite of litmus tests from existing research that we use to relate memory models to our definition of Java. And we basically define an expectation about where Java is relative to this other memory model in terms of behaviors it allows. And then we check that by running the programs using herd. So let's start with an example, and a simple example, which is x86. So x86 is a relatively strong memory model. It permits few behaviors. And what we want is what the Java memory model should do, what the jam should do, is it should permit strictly more behaviors. It is weaker in that sense. So if it's allowed for x86, it should be allowed for the jam. So we basically write this down as a truth table, just like that. And you can see that for each of the tests, if the behavior is allowed, we basically count it in the column there. Or if the behavior is allowed in one or allowed in the other, we count it in the column and vice versa. So these are the good ones, right? So this comports with our implication, right? And then the one we have to be concerned with is this one down at the bottom, which would mean that the other memory model is weaker than the jam. So in the case of x86, this is fine. In the case of ARM, we have one exception to this, which is that ARM allows causal cycles, right? Because we talked about that optimization, that example program with the optimization. So the JAM goes out of its way to forbid this, and it uses a big hammer, and it actually catches a lot of like totally reasonable optimizations with this. So again, remember our implication. We expect that these things should be weaker, but then we have this, again, this instance where ARM is weaker than the JAM. It allows this specific behavior, but this is, in fact, the example that I showed you earlier. It's called the load buffering example. And this, again, so this is the exception for causal cycle. So that load buffering example is forbidden by acyclic causality. And the idea is that the specification is very clear that this should not be allowed. It spells it out very directly. And so as a consequence, it's okay that it's here in this, this row. With C11, it's a little bit more complicated, if only because the idea that it should be similar. It's a little closer to a logical equivalence. But we have the same exception for causal cycles. So the C11 standard allows causal cycles. And again, we have these three rows. So because they're supposed to be very similar, we expect most of the tests, the behaviors, to fall in these two rows where it's the same. We have two here. These are related to release sequences. Remember I said that in Java there are no release sequence. There's no such thing. So Java is, the JAM is slightly weaker in this instance. And then again, we have causal cycles in this bottom row, which we explicitly don't allow. And so we're good to go there as well. OK, so to close, how am I doing on time?
3 minutes.
OK, good. So to close, to finish up here, I want to talk about the last instantiation that we did in Coq. We have kind of three main theorems that we proved based on some of the properties that are in the informal specification. The first one comes from some other work on kind of forbidding causal cycles and the expense of doing this. So this choice that was made in the informal specification. It basically says that if you have a causal cycle like this and you make these two reads acquire reads, then you're going to get acyclic causality for free without having to define it explicitly in the memory model. So that's not allowed. The second one is DRF guarantee. So if basically this says, this is a programming discipline, if your program doesn't have any races, if everything's well synchronized, you get sequentially consistent semantics, so which is a nice, easy to reason about memory model. This is very important in both C11 and Java, as it sort of keeps you safe from having to use the modes if you're always synchronizing your programs with blocks, for example. You don't have to think about it. And finally, remember I mentioned monotonicity of the access modes. We proved this is a theorem. We expect that in a program, if you substitute out a stronger mode for any other mode, that it should have strictly fewer behaviors, or only at least as many behaviors. OK. So the final theorem is actually kind of an interesting one. So remember we said what we said about the non-total coherence order. You would expect to be able to see in an example program the fact that two threads can actually see two values for the same variable at the same instant in time. So like if you're writing a program down, you expect to have to take that into account. This theorem that we wrote down basically says you can't construct that program for our semantics. And it's based, which is, again, surprising, but it's due largely to the fact that the semantics is so simple and the fact that we only have essentially one way to forbid executions, which is by cycles in the coherence order. I encourage you to take a look. It's like the proof is entirely easy to understand and read. So if you look at the end of our paper, that's in there. I would encourage you to take a look. Other than that, today we talked about our axiomatic semantics for Java's access modes and a little bit about how we validated it. Thank you, and I'll take questions.
If you have a program with a data race in it, what does the spec say happens? Is this undefined behavior or just non-deterministic?
I mean, it's defined. So your program should behave according to the semantics. So if there's a race, there's a large set of possible writes and combinations and things that you have to look at, right? So in practical terms, you're going to have to use access modes. It's going to be hard to reason about, yeah. Yeah, just to be clear, it is different than C11 in that regard, right, where it's undefined behavior, sure.
You mentioned that there is a difference between visibility order and it happens before. It wasn't clear. What's the difference?
That's because it's not like obvious. It's not. If you want to, I mean, so for example, the transitivity is subtle. So for example, we don't like happens before can be transitive with synchronization if given synchronization, right? So there's synchronizes with and the program order. We separate these things essentially at the top level, and the transitivity is only in this like sub-visibility relationship. So my answer is it's sort of complicated and not easy to explain, which is why it's not on the slides. But you can take a look at the paper.
Oh, okay.
Yeah,
Thank
sorry.
you.
You mentioned that ARM allows the cyclic read thing, right? So how would you compile Java to ARM that?
Good question. So that paper I mentioned here, so down at the bottom, this was in Uppsala. You can use fences. Basically, you have to look for all the places where these cycles might appear and do something. You can use I think you can use a data dependency, for example, and compile to that. But yeah, so and the overhead is not negligible given that, but that's in the paper. So, but yeah, they have lots of different modes to do that, ways to do it. Yeah, it's a good question.
If you don't tackle the out of thin air problem, what is the point of this?
The point is that the spec tackles the out of thin air problem with a big heavy hammer, so I don't have to. I think that's the short answer. I think the reason why, are you asking me why Doug Lee decided not to deal with the out of thin air problem by choosing the big hammer? That's like a meta question, right? I mean, the semantics is what it is. The definition of informal spec is very clear, so I followed the informal specification, but there's a bigger question, which is why didn't the informal specification try and deal with that? And the answer is because it's very hard to deal with it in a complete way. So the best answer we have right now is the promising semantics, but that's seemingly very hard for a regular programmer to understand and make use of.
Well, it has the advantage of possibly being sound.
This is also sound. Because if you rule it out of hand, whatever logic you build on top of it will be sound, right? And the expense is not it's non-zero, but at least we know what it is. There's work on what the expense of doing it is. I feel like I'm defending Doug's decision here, but I just formalized the informal specification.
Okay, so to keep on track, we should probably move on. Let's thank the speaker again.